the U. Now we consider the next combination, parallel combination of resistors. I consider three resistors R1, R2 and R3 connected in parallel. This connection is called parallel connection, one below the other, so that the common points, they all come together across the potential difference. That means that in parallel combination, each resistance is coming across the circuit. Means R1 connected along this way, R2 like this and R3 like this. Means they are individually connected across the circuit. Now when it comes like that, you can find the current which is derived from the supply will be reaching here and that splits up into three. That current I1 flows through R1 because the current to R1 is defined by the potential difference and the resistance R1. Like that, I2 flows through R2, I3 is flowing through R2. Now, to get the effective resistance in this case, we consider the case here, current I reaching over here is splitting up into three and they come over here and combine and flows out. So here we apply the conservation of electric charges. According to that conservation, we can see current I will be equal to I1 plus I2 plus I3. And therefore, applying Ohm's law, I1 will be equal to V by R1, I2 V by R2, I3 V by R3. As earlier said, the effective resistance if we want to find, that means if I replace all the three with a single resistance across the potential difference V, the same current I will be derived from the supply through the effective resistance. Then that I will be equal to V by RP, P for parallel. Now from this equation we get 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. That means the reciprocal of the effective resistance in parallel will be equal to sum of the reciprocals of the individual resistance. Now this combination is used to get a minimum value of resistance out of the given resistance. From this equation it is clear that the effective resistance in parallel will be less than the least individual resistance values in the combination. Now as we understood the series and parallel combinations, now let us consider a problem here, how to use equations to find the effective resistance of a given network of resistors. Now I take a simple network here of resistors how many? 6 resistors. And if I take all these are of 1 ohm, like now let us find the effective resistance of this combination across A and B. Now how we use the already studied individual combinations into this. To understand that, let us assume across A and B, when I say, we assume a supply connected across A and B. When I connect a supply across A and B, a current will be derived from this one and that current reaches over here and splits up into two, and whatever that comes over here will be flowing through this and reaching over here. By then this current reaches over here and flows reaching back here. Now you can find that the current starting from here reaches here and splits up into two. Now whatever that reaches here, the same current is flowing through all these three. Therefore, we can directly say that these three resistances are in series across these 2 points. Now, I can solve this by reducing the circuit, drawing the next step and all like that. So, if I go like that, I will be replacing these three and connect its effective resistance. The effective resistance, that is 3 ohm, as you will know, across these 2 points. Now you see that this 3 ohm and this 6 ohm across these 2 points are parallel. Because this is a common point, they are going to be connected across this. So when these two are in parallel, you can use the equation to find the parallel combination, that is 1 by Rp equal to 1 by R1 plus 1 by R2, or Rp equal to R1 R2 by R1 plus R2. Formula you can see. So when I use this formula over there across 6 ohm and 3 ohm, I get 6 into 3 divided by 6 plus 3, and that's equal to 2 ohm. That means effective of these two is now will be 2 ohm, and I reduce the figure once again. I remove these two and connect a single resistance over here, and its value is now 2 ohm. Now you can see across A and B 1 ohm and this 2 ohm and this 1 ohm comes in series. No doubt about it. Now when you take the series combination, it's the simple sum of all the three, that 1 plus 2 plus 1. So across A and B, we get an effective resistance of 4 ohm. Now this is your answer. So all that big circuit reduced step by step into the single resistance. You can show like this the effective value. Or else you name the resistors and tell that those three are in series, effective value, and that comes in parallel with the next one, like that mathematically. The best way is that reduce the circuit step by step and come to the single resistance value. Okay, that's all.